Welcome back, everybody. In this segment, we're going to talk about something called the gradient vector. And this will be an important concept for us to understand moving forward when we look at the gradient descent algorithm, which we're going to use to kind of build on our analysis of the bisection method for finding an optimum, finding the minimum of our cost function. So the gradient vector, mathematically what it is, it's actually a vector of partial derivatives for a multivariate function, so for a function that depends on more than just one independent variable. And we're going to go ahead and consider the case here of a three-dimensional function. This is a function that has two independent variables and one dependent variable. And here z is the dependent variable. It depends on some function of x and y. So there's three dimensions here. Z you can think of as the vertical dimension, and then x and y are two different dimensions in a horizontal plane. The gradient vector then is going to be given by the following. We're going to take the partial derivative with respect to x. That will be the x coordinate of the vector. And then the partial derivative with respect to y will be the y coordinate of the gradient vector. So fairly simple here to compute. You just got to remember your calculus. So take the derivative with respect to x. So whatever function that is will be the x coordinate. So the coordinate here is a function. Okay, same thing with the y coordinate. The second coordinate here is the partial derivative of the function with respect to y, and that derivative can be a function as well. Okay, and if we wanted to, we can compute the gradient at a particular point by plugging in the xy coordinates. And we can just plug those in right here, in for x, in for y. We would substitute those in here as well, and we would be able to compute a numerical value for the gradient vector at a particular point in the xy space or in the xy plane. It's possible you have more than two independent variables. Okay, if we had n variables on the right-hand side, then z is a function of x1, x2, x3, x4, so on and so forth. In the case where we have n independent variables on the right, then the gradient vector of f, it would be the partial derivative with respect to each one of those variables. The gradient vector would also have n elements. The first element here is the partial derivative of f with respect to x1, then the partial derivative of f with respect to x2, so on and so forth. Okay, we're going to keep it fairly simple here in three dimensions just because it's easier for us graphically to represent things in three dimensions. And that will also be the case when we move on to our gradient descent segment. But we're going to consider the following function here. We'll just go through a numerical example of calculating the gradient. So we got x squared plus y cubed plus 4xy plus y. And in order to compute the gradient, again, we're going to calculate each element, right, each coordinate of the gradient. And each coordinate is going to be a function corresponding to these partial derivatives, right? The x coordinate here is going to be the function that we get when we take the partial derivative of f with respect to x, treating y like a constant. Okay, so we should be able to just use our basic power rule to do this, not super complicated calculus here. And we will get 2x plus 4y, right? Any constants with y in them that don't have an x go away. So that y cubed goes away, that y goes away, and we're treating y like a constant otherwise. If we take the partial derivative with respect to y, okay, we will get 3y squared plus 4x plus 1. So the gradient vector will have the partial derivative with respect to x as the x coordinate, and it will have the partial derivative with respect to y as the y coordinate. So here it is. Okay, here is our partial derivative with respect to x, boom, boom. Okay, here is our partial derivative with respect to y. All right, now, why all the calculus? Why is this important to understand? Well, it's important to understand more from a geometric perspective when we're thinking about this search algorithm, right? We're trying to search in some space, xy space, for some optimal parameters that minimize a function. And hopefully you remember from some calculus that the derivative information is very useful in identifying max or mins. So the gradient vector, right, given this vector, okay, we can actually compute a numerical value for it by plugging in particular points in the xy plane. For example, if we wanted to compute the value of the gradient vector at this point 1, 2, where x is 1 and y is 2. Okay, all we would do is we would take 1 and 2 for x and y, and we would substitute those in here. X goes in there, y goes in there, and we would be able to compute that coordinate value for the gradient. So if we do this, okay, you'll note, what do we get? Well, when we looked at the first coordinate, 2x plus 4y, and then we went ahead and plugged in the actual values, we plugged in a 1 for x and a 2 for y, that is where we are getting this value of 10. Similarly, that 17 coordinate, that comes from these terms over here, 3y squared plus 4x plus 1. We again plug in the x coordinate of 1 right there. We plug in the y coordinate of 2 right here, and that gives us the value of 17, the value of the gradient's y coordinate. Okay, now I mentioned before that understanding this is important really from a geometric perspective. So let me go ahead and talk about that a little bit. Recall that geometrically a gradient, or rather a vector in general, measures both a direction and a magnitude. There's a directional component and there is a magnitude. And the gradient vector is important in that the direction the gradient vector points, okay, from a particular location is the direction in which the gradient, or sorry, the direction in which the function increases most rapidly. And we refer to this as the direction of steepest ascent. Okay, so if I'm somewhere on the function and we calculate the gradient and I look at the direction the gradient tells me to move, and I move in that direction, I will move up the function at the fastest rate possible. Now, in order to really help think about this idea, it's important for us to introduce a concept known as the level curves of a function. And this will be useful specifically in the case of a three-dimensional function that we're going to look at momentarily here. And we're going to relate this concept of level curves as really being analogous to the idea of a contour map or a topology map that you may have come across in your days looking at, maybe a GPS map or a road map or something. But you might recall seeing an image like this. Okay, and there's a bunch of what looks like concentric rings, right? A bunch of non-overlapping rings here. And those different rings, okay, we're going to refer to those as the level curves. Okay, those different level curves, okay, again, we can think of this as being analogous to this contour map. But what they allow travelers to do here is, even though you're looking at a two-dimensional map, you can recognize the underlying three-dimensional structure of the world. Right? This is a two-dimensional projection of a more complicated three-dimensional world captured in this contour map. And the map uses what looks like concentric rings to identify different levels of elevation, or rather to help you identify when you're changing different levels of elevation. So here is a slightly different perspective of how you can take a three-dimensional picture, if you will, and kind of compress it down into a two-dimensional representation. Okay, so we have in the top image here, we have an actual, like what looks like a mountainous structure. You can think of that's our function. We maybe want to maximize it. We want to get to the top. And you'll notice we can see here there are different levels where the elevation is held constant. For example, in the top image, here is the level curve along that line where the elevation is equal to 1,100 feet. And note, we can look straight down at the projection, the compression of that three-dimensional image in the space below, and we can identify that same level curve down there. Right? That is the level curve corresponding to an elevation of 1,100. All the points on that level curve have the same z value, have the same vertical axis value, have the same elevation. If we went up in elevation, we can move up to this other level curve that corresponds to points that are all on a higher level of elevation at 1,200 feet. And we can also represent that in the compressed image below, this contour map in 2 dimensions. So the idea here is going to be the following, that the gradient is going to provide us information in this 2-dimensional map below. Okay, so we're going to be navigating down here. This is going to be our map. The gradient is going to tell us which direction to walk in if we want to climb to the top of the function the fastest. If I wanted to climb to the top of that mountain, I can pick any point. I can put myself there, right? I can pick any point in the two-dimensional map. I can put myself there. And the gradient vector, what that will do is it will tell me in which direction I should walk in this space to get to the top of that mountain as fast as possible. Okay, so mathematically, that's why the gradient vector is useful for us. We're going to be looking at this topological map, okay, and the gradient vector is going to point in the direction from where we are, okay, to where we should go if we want to go to the top of that function as fast as possible. So let's go through and look at an example here. Here is a three-dimensional function where z equals x squared plus y squared. And let's go ahead and plot the level curves here of this function by locking in a particular elevation for z. So we're going to choose some number for z. So we can think of z here like really as like the elevation. Okay, that's the vertical axis that we're measuring elevation on. And what we want to do is we want to look at all the xy points at the same elevation. So we want to look at all the xy points on the level curve. Okay, and if we choose different values for z, we can move to different elevations. We can move to different level curves. So let's go ahead and look at the level curve where we're looking at all the points at an elevation equal to 1. Okay, so we're going to take x squared plus y squared, and we're setting it equal to a z value of 1. And if you look at this equation carefully, I picked this example here because you might remember this from geometry. This is an equation of a circle. Or maybe your algebra class. Okay, this is an equation of a circle centered at the origin with a radius of 1. Okay, that is what this shape is here. So it'll make it fairly easy for us to draw what the contour map looks like. The contour map should look like a series of concentric circles. So here is the contour map for z equals 1. Okay, again, it is a circle with a radius of 1 centered at the origin. And to show that this is the case, if it's really have a radius of 1, then we know in any direction, whether it's north, south, right, or east-west direction, the direction from the origin to the circle, if it has a radius of 1, should be equal to 1. So we know what those points are where that circle is intersecting the x and the y axes. Okay, and we can verify that the equation up here holds true. We want to make sure this equation holds true. And an equation should hold true if we plug in any point on the function satisfying that equation, right? So if I plug in a 1 for x and a 0 for y, we get 1 squared plus 0 squared, that is equal to 1. And that definitely satisfies this equation here. And we can see the same thing in any of these other easy points to check here, right? 0, -1, that's down here. You square -1, you get 1, right? So 0 squared plus -1 squared also equals 1. So all of these points on that circle, these are all at the same elevation. And that elevation is when z is equal to 1. Okay, now we could consider moving up to a higher elevation. Let's suppose we wanted to move up to an elevation of 4. Okay, now we're going to set z equal to 4, which means we want to plot all the points where x squared plus y squared equals 4. And again, that is a concentric circle. Okay, it is a circle centered at the origin, but it now has a radius of 2. The radius, in fact, is the square root of the z value, it turns out. You might remember that from your algebra or geometry class, but if not, no worries. Point being, okay, we could draw the level curve here for z equals 2. Or rather, sorry, z equals 4. Okay. This should be a 4 here. Not a 2. Should be a 4. All right. And we can again check a couple points, right? We know 2, 0 will be on that level curve if this is indeed a circle with a radius of 4. So you can plug in, a 2 for x there. You can plug in a 0 for y, and you will get 4. So we should be in good shape there. You can check some of these other points that are fairly easy to check: 0, 2, -2, 0, 0, -2. They're all on that same level curve. They're all on that same part of the contour map. We could even think about drawing more levels. Right here is one where we've also included the elevation level z equals 9. Right, so this is the entire contour plot for this function. We get a sequence or a series of these concentric circles, and these rings can help us. Right, if I know where I am on this ring, on this map, I can figure out which direction I would need to move if I wanted to move up the function to higher elevation or down the function to lower elevation. Okay, so if we wanted to move towards lower elevation, we can move closer towards the origin, right? Want to move closer in towards the origin, lower elevation. But if we move away from the origin, moving away from the origin is going to move us to higher elevation. So the idea is we can use this contour plot as a simplification of the true reality, which is we actually have a three-dimensional function that looks like this. We are just looking at it, like straight down from the top, as if we've looked at different slices of it horizontally across the XY plane. So this contour map is allowing us to navigate this three-dimensional function here. Okay, so that contour map of those level curves, again, what are they? Those level curves are just a two-dimensional projection of the more complicated three-dimensional function, right? But rather than using 3 dimensions, we can look at it in 2. And the level curves are really what we would get here if we thought about slicing this function, right, across the XY plane. Here's a slice very low. Okay, here's a slice up a little higher, higher, higher. And if we took those slices and we compressed them together, what would we see? If we look straight down, we would see a series of concentric rings, concentric circles, just like we had suggested before. Now, what good is the gradient vector? How does it help us navigate this map? Well, as we mentioned before, the gradient vector points in the direction where we move up the function the fastest. It points in the direction of the steepest ascent, the most rapid increase in elevation. And we can use the contour map in conjunction with the gradient to help us think about which way we should move if we were interested in going up the function, if we had to maximize it, or more importantly, for our case of cost minimization, if we had to walk down the function and minimize it. So let's go ahead here and take a look at our function. We have this x squared plus y squared function. If we take the gradient vector, right, going to have 2 elements. The first element is the partial derivative with respect to x. So if we take the derivative of x squared, you get 2x. Y is just treated like a constant. So our partial derivative with respect to x is just 2x. Similarly, if we take the partial derivative with respect to y, x squared is a constant, so that becomes 0. And then the derivative of y squared with respect to y is 2y. So our gradient vector here should be 2x as the x coordinate and 2y as the y coordinate. And what we're going to do is we're going to look at the value of the gradient vector if we plug in our location on this map. Okay, so we're going to pick a point. We're going to pick some xy coordinate on the map, and we're going to calculate the gradient vector. And the most important thing for us to think about is the direction that it points. Okay, so let's suppose we are standing at the point with coordinates 2, 0. And that's a point we saw before. 2, 0 was on that ring where we were at an elevation of z equals 4. That was right there. And if you plug in 2, 0 into the gradient vector, right? 2 goes in for x, 0 goes in for y, then you should compute that the gradient vector is equal to 4, 0. And what we're going to do is we're going to plot that point at 4, 0. And then the actual vector itself is going to be a line from the origin to this point at 4, 0. So I'm suggesting here that if we were standing at our point 2, 0, so we're standing here at 2, 0. If we walk in the direction of 4, 0, so if we walk in this direction where that purple line is pointed, that purple line is the gradient vector. If we walk in that direction from 2, 0, that will move us up the function as fast as possible than if we walked in any other direction. This is saying we should walk directly to the right, directly east. That is the gradient vector. The gradient vector points in the direction of this contour map that moves us up the function as fast as possible. Okay. Try one more point. Okay, let's suppose instead our position was at 0, 1 up here, which we know corresponded to an elevation of 1, z value equal to 1. Okay, we can do the same thing. We can plug in 0 for our x value, we plug in 1 for our y value, and then we would get the gradient vector, which is now equal to 0, 2. And we can see that if we were, again, standing, if our location was here at 0, 1, okay, the gradient vector says if we wanted to move up the function the fastest, we should walk directly north. We want to walk in that direction. That is the direction of steepest descent relative to where we were standing at 0, 1, our current position. Right? So again, that gradient vector is telling us here that if we want to move up that function, x squared plus y squared the fastest, we better move north. We better move straight up in the y direction if we wanted to increase the z value most rapidly. Just to wrap up here, a couple things. So the gradient descent, this is a different algorithm than the bisection method. We'll talk about the actual algorithm in the next segment. But the bisection method was an algorithm that allowed us to search for a function's optimum in just a single dimension. Okay, the gradient descent is essentially going to be a generalization of this idea that allows us to search for the optimal parameters in a situation where we have a high dimensional set of parameters to look for. And it functions very similarly with respect to the bisection method and at the slope information of the function. Right? The gradient contains the slope information, the information of the derivatives and all the different directions you can walk. That is going to be used to guide our update rule at every iteration in much the same regard that the slope information was used to guide the update rule in the bisection algorithm. So we will pick up with that in our next segment, discussing the ins and outs of the gradient descent algorithm. Hope that was informative. See you soon.